This is Joe Breeden. I appreciate you joining me today. We are going to be talking about some of the research we've been doing into using quantum computing and classical methods and applications we found for that. The work I'll be showing today was done by myself and Jeannie Leonova here at Deep Future Analytics. And I have to say this work started just from the question of what is it good for? We know that quantum computing sounds cool, and you will see anything that has humorous content in this talk is all credit to xkcd.com. They have the best scientific cartoons out there, so I highly recommend that. But I just want to point out that there's a lot of hype, of course, around quantum computing. My own thesis work years ago was in chaos theory, and that was a field that saw a lot of hype. I once heard about a book of using chaos theory in business management, which is complete nonsense. and you'll find nonsense everywhere. So really our goal was to be able to tell the difference between the promise and the nonsense. The typical nonsense is quantum computing makes everything faster. Well, that's not true. It makes certain kinds of problems faster. And I think the best way to think about quantum computing, when we get to the point where we have a quantum chip that we can put on a computer, it will sit right there next to a graphics accelerator chip and various other specialty chips that all work together. Quantum computing is a kind of specialty processing that for certain problems can make things much faster. So that's what we wanted to look into. Specifically, we wanted to ask the question, what could be a game changer with quantum computing? What can we do with it that we cannot do today? There's a lot of good talks, a lot of good research into quantum computing, quantum convolutional layers in neural networks for faster image processing. Sounds cool. Quantum computing for singular value decomposition, and there's a whole list of things you can mention. And in general, quantum computing adds dramatic speed up if you have a closed form solution. If you can say, here is the mathematical object I'm trying to optimize or find the root of or solve in some form, then that's a case where you have some hope of getting a dramatic acceleration. But will it change our industry to have a faster neural network or a faster singular value decomposition, things like that? It's never a bad thing to have things go faster, especially when you're processing very large volumes of data. But our processing to build models is something that happens offline. You build the model, then you have to validate the model, and then it has to go through documentation and validator review, audit review, regulatory review. That model development timeline can take anywhere from 6 months to 18 months, depending on the tech stack of the organization. Some are a little quicker, the leading edge, but it doesn't seem to me today that that's going to change our industry to be able to accelerate the model build part of it, because you still have all the rest of that timeline. So as we were thinking about what could you do today that you couldn't do before, that's where we started thinking about account level distributions and not just looking at a mean to be estimated, an average to be estimated, but to really understand uncertainty in a way that we haven't before. So that's what I want to look at. And in doing so, we'll go through a specific example that we built, a certain kind of model where we could understand all the uncertainties. And then we use those to do both classical Monte Carlo simulation and to look at quantum Monte Carlo simulation. Now, I will be honest up front. look at. We did a lot of library research on quantum computing. We studied how the code is written. We looked into scaling laws and architected what would the solution look like, but we didn't implement it because to do it the way we want is still beyond current hardware. And a toy problem would be cute, but doesn't really get us anywhere specifically. Just wanted to see proof of concept where that would be. Now, account level distributions. Um, we deal with distributions when we're talking about things like economic capital. That's always good, but and there are various other uncertainties in our portfolios that we look at. But when I think about the big unknown, it's taking all this down to the account level because individual accounts are different. Um, Basically, the use of account level pricing, if we think about this, what we call account level pricing is essentially bucketing accounts into certain bins. I think organizations who admit the uncertainty in their models wind up with 5 to 10 bins, and that's where their pricing falls. Things like a FICO score, if you look across bureaus, you easily get plus or minus 20 points on consumer FICO scores, bureau scores, which is why bucketing bureau scores is a common way to deal with that. But I think the best way to think about what's happening here is that not all accounts at the same score are the same. On the bullet point here, I've got a 680 FICO score for a full file account, meaning that maybe their credit utilization is not perfect, and you've got plenty of history to show that, versus 680 FICO score for a thin file account. In fact, maybe 620 would be a better reference point here. A lot of thin files, you just don't know anything about them. So that thin file could be a good consumer if you knew more about them. The uncertainty is quite wide. Whereas a full file, low FICO score is somebody that you've got a pretty good idea is a high risk. And so they may have the same mean expectation, but very different uncertainties. And if we really want to do account level pricing, uncertainty, cost of funds, some of these things should be part of that calculation. So I wanted to understand how to get these things down to that account level. So for a baseline model, we used a model that we know well. And if you've heard other talks, we have given talks on what we call multi-horizon survival models as our preferred framework. It's basically start with a vintage model. We use age period cohort estimation to understand life cycle, environment, credit quality. Then you remove the credit quality aspect and essentially build a survival model in its place. And you build that survival model so that you've got different coefficients for different forecast horizons. That way, what you're really doing is combining aspects of behavior scoring and roll rate models with vintage models. Specifically, that's what we were trying to achieve in developing this framework. Age period cohort models give you a life cycle and environment. The life cycle will have uncertainties. The scoring coefficients will have uncertainties. And the environment, the historic environment, we'll use to calibrate a diffusion equation so that we can understand the environmental uncertainty going forward. So every one of these steps has uncertainties. And because the score is account level, and your forecast for a specific account will have a unique confidence interval, we want to be able to combine all these to understand the entire risk distribution for an individual account, for each individual account that we model. So I have been a big fan of vintage models for a long time. And I was pleased to see that Steve at XKCD also understands the importance of vintage analysis. The slides you're going to see, what we did was to apply this approach to both probability of default and probability of attrition. We have Freddie Mac data that was analyzed. We selected just prime borrowers, 360-month term, nationwide, taking, not trying to do it state by state in this case. So taking a slice of that data to simplify the problem a little bit. When you do that, you get a result that looks like this. The graph on the left is what a vintage graph looks like. We actually use monthly vintages, but to graph it, an annual vintage is easier on the eyes. So here you've got each line is one annual vintage, and you can see the couple of previous recessions. If I updated this graph today, you're going to see a pandemic recession in here as well. And you'll notice there by eye, if you line this up different ways, you can figure out roughly what the life cycle is. You can see differences in credit quality. So that's what age period cohort analysis does, is to split this into three main components: a function versus the age of the account that we call the life cycle. So this is the monthly probability of default. A function versus calendar date, which is a measure of the environment. And you'll see certain spikes on here for special events that happen. Hurricane Katrina is back here. And then the broad sweep through here is going to be due to recessions and expansions. And then the third piece is the credit quality component, where you can see periods of higher risk originations back in 06, 07, 08, very high risk mortgage originations. We have a paper on that jointly with Jose Canal Cerda of the Philly Fed that we published back around 2016 that explains how adverse selection drove a lot of this. Most recently in mortgage originations, the credit quality has deteriorated as people have gotten more open in their lending criteria. We also think that there is the beginnings of an adverse selection event happening now because of inflated bureau scores due to checks in the mail to all consumers, regardless of their payment ability. And so when you get inflated FICO scores like that, it means that FICO loses discrimination. So you might think you're originating a 680, but really they might have been a 640, if not for the check in the mail. We also know from this prior analysis that as interest rates rise, the financially conservative borrowers, the value shoppers, tend to drop out of the market, and it leaves the rest of the pool as riskier borrowers in the market. So this year could be a period of increasing adverse selection. We'll probably try to give a talk on that in the next month or two. So with these three components, the life cycle is usually quite stable through time once you've normalized it for these other two effects. We will keep that in the analysis. We'll take the environment and calibrate a diffusion equation to this. And then we're going to replace this vintage level risk measure with an account level behavior score. So that behavior score, we call it a multi-horizon survival model because at each future forecast month, we estimate a separate set of coefficients. We do this because when you look at delinquency, the dependence on the delinquency is very nonlinear. That a early delinquent account today usually has peak risk of default some months into the future, whereas a highly delinquent account, month 4 or 5, is likely to default right away. So this kind of roll rate effect can be captured in the behavior score if you estimate coefficients that are different for different horizons. And once you get beyond around month 6, things start to settle out. By the time you get to month 12, the coefficients usually have pretty much saturated. These coefficients are estimated with life cycle and historic environment as fixed inputs. And we also have a coefficient here for vintage dummies. These are residuals. This is essentially an adverse selection coefficient. So when we look at macroeconomic uncertainty, this is where we use a diffusion equation. We use what most economists use. The best known process for this is an Ornstein-Uhlenbeck equation. And we use a second order equation, which means we have diffusion in both velocity and level. So that if things are trending up, they're more likely to continue trending up. Um, and over time, the mean is going to relax onto the long run average, but the confidence intervals around this, they're not estimation confidence intervals. They're really the distribution of where the environment could go. So this is going to spread with time. And you can see there's an oscillation here due to seasonality. So as we look at the range of possible futures, we've got a mean expectation. The long run average here is 0. And then we've got this range of possibility that grows with time. This is one way to do economic capital. We have papers on how to do economic capital where you will see that a point in time estimate for economic capital would look at the first 12 months of this. If you want to do through the cycle economic capital, by the time you get out to about month 36, this distribution will converge to what a long run distribution looks like. Now, to take the uncertainties, we're going to look at Monte Carlo simulation. And when I think about Monte Carlo simulation, I think very much about this comic, which is about creating a complex algorithm that is, I wouldn't say prone to failure, but Monte Carlo algorithms can be a very complicated way to solve things. There's no doubt. We wouldn't use it if there was another way. The challenge, I'll go back to this previous slide. The challenge is that to get to a calibrated outcome, we want to be able to say, what is my 99% confidence interval on a final lifetime loss distribution? To get there, I'm going to have to take the distribution at every month that I've got here and combine them. And combining those distributions along with all the rest of the math is too complicated for a closed form solution. Instead, what we'll have to do is sample from these distributions as well as sampling from the other uncertainties. So you wind up with a Monte Carlo approach. And this is what that looks like. We have a competing risks model because we modeled both PD and conditional probability default and conditional probability of attrition. Conditional means that the denominator for PD and PA is accounts that were active in the previous month. So if I'm doing a lifetime loss forecast, by the time I'm getting out to 36 months, 60 months, that denominator is getting quite small. That's why the life cycle tends to keep going up, so that if you're still on the books in a mortgage portfolio 10 years into the future, that means you didn't have the ability to repay. The risk is actually increasing because the better credit risk consumers usually refinance before that point. So the life cycle has a confidence interval at every age. The environment has the distributions that I was just showing you. So for every time, there is, I'm representing this as if it was just the width of a normal distribution, but in fact, we have that entire diffusion equation distribution, whether it's normal or not. And then you've got the individual account risk that comes from the scoring component at each point for each account. When we run that score component, there will be a unique forecast uncertainty for that. Now, in log odds space, life cycle, account risk, even environment are all roughly normally distributed. So you can get to the mean very easily by just adding these up. And the confidence interval, the standard deviation around that is very simple to compute. But this is at a single point in time. And so as you go to further moments in time, these things will change. And in fact, Note that even the score component is a function of time because those coefficients are a function of the forecast horizon. So in a situation where you have a normal distribution in logit space, there's a word for that. It's called a logit normal distribution, and there's a closed form solution for what that distribution looks like in normal space. I mean, shouldn't use that word, but in the probability space, it looks like this. Now, the challenge is that you can't easily combine these. I have a distribution like this at every time step. So if I want to combine multiple time steps, the only way to do that is going to be with sampling, with a Monte Carlo simulation. So the calculation of the final result that I want to get to, basically, my stated goal in the beginning was account level pricing. What I really want for account level pricing is account level yield and uncertainty in the yield. So to get to an account level yield, I want to estimate the cash flows. What's my risk of charge off at each month? How much balance is going to go with that charge off if it happens? Because if they haven't charged off until month 24, presumably most of the prior months they made payments, so that that loss, the exposure at default is going down until they get to an actual charge off event. I also have the revenue side of things. So that's where the probability of attrition is important as part of this cash flow, that I can see the risk that the loan pays off and get the effective life of the loan. So the way we write this is that we have a conditional PD, a conditional probability of attrition. At each month in the forecast, I have a probability that the account survives. So at month 1, the probability that it survives, or I should say at month 2, did it charge off in month 1 or did it pay off in month 1? If not, then it will have survived. And so that probability of survival might be 0.99, 99%. And then this iterates, of course. So then at month 3, you have that 0.99 times the new adjustment. At each one of those months, I'm taking my conditional probability of attrition, multiplying it by the likelihood of survival to get to an unconditional probability of attrition. And the unconditional probability of attrition, I can simply sum up over the forecast horizon to get to a lifetime PD. Now, this is not the entire yield calculation. Quantum computing is not ready for that, definitely. We wanted to bound the problem first by looking at PD and PA, but ultimately we would do the same things on the balance side of things. Now, when we did this, I'll step back. So we ran a Monte Carlo simulation where for each of these elements, we sample a value. At each forecast step, sample a value of life cycle within this distribution, sample probabilistically, sample the environment, sample the score, combine these things, and then do that for every time step to get a final lifetime PD for one simulation. And then we do that calculation 10,000 times to get to a distribution that looks like this. And this distribution is the multiply of logit normal distributions. So there's no theory for what that's going to look like exactly. But when we compare it to lots of different possibilities, we find that it actually fits quite well to either a log normal distribution or a beta distribution. So that's quite interesting. What it means is that we can either do the 10,000 simulations to understand what the tail risk is, or if we have a good idea of the shape of the distribution, we can do something more like 50 simulations to measure the parameters of the distribution in order to understand what that tail looks like. So knowing the shape of the distribution in advance can dramatically accelerate this account level risk assessment. Now I'm actually showing two different accounts here. This is a delinquent account that has you can see the average here is about a 55% chance of charge off in the life of the loan, with a pretty wide distribution between 0.4 and almost up to 0.8 if you're looking kind of out at the tails here. The other account is an account in good standing, and you can see that its risk of default currently is around 0.0065, so less than 0.5%, well, around 0.5% chance of default. And the width of this distribution is of course in probability space much more narrow. It's more proportional to the risk. But what we've got here, two very different levels and widths of uncertainty. These are not accounts that would need the same amount of economic capital, obviously. And in fact, economic capital is usually just referring to that environmental uncertainty. We've also got the scoring uncertainty in here, which is kind of your model uncertainty, as well as the life cycle uncertainty. So we could add as many different uncertainties in this calculation as we want, but the ones we've considered are the ones that are really most account level specific. Okay, so we've already learned something from this that we didn't expect coming in. We assumed that the reason, I mean, who out there is doing account level risk simulations at point of sale for a mortgage? I would say no one that I've ever seen. And if the assumption is that you would need 10,000 simulations for every account, that takes minutes, can easily take 5-10 minutes, depending on what you're trying to do. That's too long for a loan origination system. But if you know the shape of that distribution and only need to estimate these parameters, then it's down to a couple of seconds. So why don't we do this? You know, we know how to make these models. It's a matter of being able to add this to the loan origination process and considering uncertainty as a dimension in pricing when we're making an offer for a loan. Now, all of that is classical, and I'd say that we learned something in just setting up the classical calculations about how to accelerate things. We assumed we couldn't do this in the beginning without some quantum computing acceleration here, but in fact, we already learned enough to make it plausible with just classical computation. I have seen other articles that have done the same thing, that in the process of learning how to do something with quantum computing, they've learned how to do it faster classically. That's a good thing. Quantum computing gives people a different way of thinking about a problem, and there are times when we get those insights. So that's all great. But we want to go in and look at how we might do this with quantum computing. This slide is called Quantum Monte Carlo Simulation, and there's an unfortunate term that quantum Monte Carlo simulation in the physics literature refers to Monte Carlo simulations of quantum mechanical systems, as opposed to what we're trying to do here. So it's Monte Carlo simulation with a quantum computer. Now, if we get back to why use quantum computing here, I have to be honest, you know, it's cool. I wanted to understand what we could do with quantum computing. There's this fear of missing out, right? Can it do something that we need to know about that we wouldn't be able to do otherwise? But also, it's just really fun to look into. Again, as they point out well in XKCD. So a little on quantum computing basics. There's a lot of ground we could cover here. I would say, unfortunately, the literature on quantum computing is written by physicists to a large extent, and they've used physics notation where things could be described in more generic language. So you'll see what's called bracket notation on how quantum computers work. It's just a shorthand notation for what you could express with statistical integrals. But in any case, a quantum bit, a qubit, is something that instead of being either 0 or 1, it has a probability of being 0 or 1. And those probabilities, actually, the probability comes when you go to sample it, but the state of a qubit is measured in terms of amplitudes, and it's the sum of square of the amplitudes that's going to be equal to a probability of 1. So amplitude squared equals probability. This winds up being really important because you're doing the calculations on amplitudes, and yet you do the final observation in a probability. Some of the speedups that we'll get are largely due to this, that when you're working in a space to get an answer that in the end is squared to get to a final result, that square winds up being part of the acceleration that we're getting. So this is going to be a key point in quantum Monte Carlo simulation. But to get to beyond 1 qubit, you talk about an M qubit register. And this is where you have a combination of qubits where, think about it as a matrix, the possible state of these two superimposed gives you a number of states. So it's basically the number of qubits squared gives you the dimensionality of this thing, or it's 2 to the m, actually, not squared, but 2 to the m. So if I want to be able to do calculations on a number that has that would be equivalent to being stored in an 8-bit classical calculation, I can do that where I only need 2 to the m equals to 8. So in this case, I can do it with 3 qubits instead of 8 bits. What I'm going to do with these registers is to store a distribution in them. So think about an M qubit register. If I have something like an 8 qubit register, then that would allow me to represent a distribution with 2 to the 8 sample points, which is quite a lot. So I could do a pretty fine-grained representation of a distribution where the sum across all that is going to be equal to 1. So this is what I mean when I say I want to do calculations on distributions. I want to use these M qubit registers to represent my distributions and do calculations with multiple registers. Also note, copying is tricky in a quantum world. And in fact, in this problem, this is an essential point, that if I need to use the same value at multiple points in my calculation, then I can't copy it. Because if I copy the distribution and then you think about sampling it at the end, I'll get 2 different samples. But if the math expects me to have the same value, what I need is entangled samples. And entangled meaning that I'm going to get the same value from both distributions that I use in 2 different parts of the calculation. And in the quantum literature, that's called a controlled gate, that I'm going to make sure that when I copy this distribution, they're tied together with a control gate so that they give me the same answer. Now, the approach to doing this, there is no closed form solution to this calculation. So that's why we're talking about Monte Carlo simulation. Fortunately, others have come before us on this. There's work by Egger and others who used quantum computing to do value at risk calculations with Monte Carlo simulation. And so that value at risk calculation is about computing a distribution and measuring at a sample point. What they were doing is to have distributions on different products and a correlation matrix between them, combine those distributions and then measure in the tail. So they have a single time step, but multiple different product distributions. What we have is multiple time steps, multiple distributions of the same account. So we are going to combine them up through time using a certain formula, as opposed to combining them independent of time. So it is a different way to think about it, but it's going to use that same structure that they had used. The algorithm that we need, so we need to create a quantum algorithm, and I'll follow their notation, which is this quantum algorithm is equal to U times S times C, where U is the register load, loading the distribution onto a register, summing the registers to get to a lifetime PD estimate. And actually S does all the calculations, including the sum. And then C is that we need a condition bit. We need a bit that says, for the solvency level that we want, is the result higher or lower than that? Because remember, at the end of the day, in quantum calculations, there's always going to be a single number returned. We don't get the whole distribution. We measure one sample and we do it again. Now, the sample points, the way this is done, if all we were doing was measuring one point and building up that final distribution, we'd have no advantage compared to classical calculation. The trick is that there's something called a quantum amplitude estimation algorithm. And this is a way of setting up the problem as in a matrix structure. And really what you want to do is solve for the eigenvalues of that matrix. And there's a quick way to do that using a quantum Fourier transform, or in this quantum amplitude estimation algorithm. And basically, I'm not giving you all the details because it takes a lot of time to go through all those details, and they're published well in some of these papers. But at the end of the day, this process that they're going through takes advantage of the fact that the calculations are being done in amplitude space instead of probability space. So you can estimate the properties of that distribution much faster. And you basically get a square root of the number of simulations type of acceleration. So what that means is that if I wanted in classical computing to get a certain accuracy with 10,000 simulations, I would only need the square root of that on the order of 100 simulations in order to do the same calculation with quantum Monte Carlo. Okay, so that is the big improvement in speed that we're looking for here. Now, let me make a few comments here that there are challenges with this, that the algorithm for loading the distribution into the quantum register, if it was a normal distribution, there's a log m algorithm for rapidly loading a normal distribution, but a logit normal distribution doesn't satisfy those criteria. So at the moment, there's no known algorithm to efficiently load that distribution. It means that the amount of calculation it takes to load that distribution is equal to 2 to the m, that every one of those parameters has to be set. So that's slow. That doesn't help things here. There are other things in here that slow things down as well. So for example, if we want to do this with competing risks, you can still do quantum algorithms for Monte Carlo with that competing risk case, but the survival probability that I mentioned, at each point, at each time step, you need to know what's my conditional probability of default, but also if it didn't default, then 1 minus that is going to fold into my probability of survival. So every one of my conditional probability distributions has to be used in two places, one for computing defaults and one for computing survivals. And those have to be entangled. And that means that the number of registers you need is going to grow linearly with time, with the number of forecast steps. And that quickly exceeds what we have available in quantum computers today. So that's a challenge. And I'm not even bothering to mention the noise in readout from quantum computers. There's a lot of noise in today's machines, but progress is being made there. And of course, progress is being made in the number of registers. So this is not to say it can't be done. It's just to say that it's a challenge today. Now, what I don't have in the slides here is that, and we do have a paper on this we can share, is that there's another way to do this. We looked at, instead of doing a conditional probability of default, what if we make the original model an unconditional probability of default? And so that would mean that we do the age period cohort decomposition where the denominator is booked accounts, not accounts in the previous month, and your life cycle is going to come down as the account ages because there's less probability of default because you're folding together attrition and default in the same model. It's not an ideal way to do it because the dynamics of attrition and default are different. It means that your score is going to be combining elements of attrition and default in the same score. But you can do that, especially if you have lots of data. So let's say that you instead make a direct model of unconditional probability of default. In that case, you don't need the entangled calculation, and you won't have linearly growing demands on the number of registers. In fact, you could do it in place. So that is something that could be done today, and it could give you not only the speed up, but also a sufficiently small footprint in terms of number of quantum registers that it could be done. So quantum supremacy, people talk about, this is where you can prove that a quantum algorithm is doing something faster than a classical algorithm could do. You can see a lot of things in these slides that come out as square root of a certain number of calculations. So you need a big problem to show quantum supremacy. And we probably would get there if we did enough time steps, like with a mortgage, and if we used enough resolution in our registers that the problem is a challenge, and the quantum computing will be beneficial. Knowing the shape of the distribution is useful even in quantum computing, because then instead of doing the quantum Monte Carlo simulation to understand the shape of the distribution, all I need is the shaping parameters from a beta distribution or a log normal distribution. With those shaping parameters, I then know everything I need to know. So if in the classical case, we could get that down to 1.7 seconds, we could get that even faster with quantum computing, which means now I can bring in the rest of my yield calculation. I can expand the problem just beyond looking at lifetime PD. So this is what we've seen so far. These are my conclusions today. Now, hopefully, I know that in advertising this talk, some people reached out to me who have a background in quantum computing already, and they were intrigued. I hope some of them managed to join us. They may have questions or experiences to share. Certainly, I'm willing to share what I've learned. So I want to open up the floor to just any questions you've got. We can talk about the work we presented here or quantum computing more generally, but I appreciate your time today in going through the work we've done so far. So I'm going to pause a minute and give people a chance to think about their questions. I'm just reviewing the chat window here as well. Okay. One question was about the model type that we used, the extent to which this is specific to the model type we used. And I would say the yes and no. We chose a model type that was a cash flow model. because in the problem we were looking at, we need the details of a cash flow model to get to a yield analysis. Would you want to do something like this if all you have is a credit score? There's no economic environment being considered, there's no life cycle, it's just a classic credit score. Probably you don't need it, because in a simple logistic regression calculation, you have forecast uncertainty. Now there's some dispute about what that confidence interval is in a logistic regression forecast, but there are some answers you could come to on what that distribution is. So in that case, that problem's simple enough. I don't think you need it. I think where it gets interesting is in these cash flow calculations. And then the case there is going to be, do you know enough to understand the uncertainties? So one challenge might be, we see a lot of machine learning algorithms that are not focused on confidence intervals. If you take a tree type of algorithm, or even a random forest type of approach where you've got multiple trees, um, those are often used just to get to an outcome, 0 or 1, or you can average across multiple answers to get to a probabilistic outcome, but then there's an added step of how to get to a distribution. So um, a lot of the machine learning algorithms I've seen, there needs to be some extra work done to understand the confidence interval around a single forecast point. But if you do that work, then this should apply as well. Okay. Any other questions here? I would ask a question of the audience we've got here, which is whether anybody on our call today has thought of areas they want to use quantum computing in, or if they've tried. If you want to type comments, or I can even take someone on off mute if they'd like to share an experience, but I welcome anybody who has had some experience looking into that. Okay, I'm looking through our attendees to see if I'm going to call anybody out. Okay. Well, I guess we will leave it at that. I appreciate you all joining today. Don't have to be shy if you have any questions, but if you come up with questions afterwards, please feel free to let me know. We will make the presentation, the recording, available within about a week, so you'll be able to find that on our website. So thank you all for your time today, and we will probably have our next one in a month or 6 weeks from now on adverse selection. So I hope to see you again then.